All right, so yesterday we started 2.5. We took a look at one type of substitution. In particular, we looked at substitution into homogeneous differential equations. And the thing that we were looking for was ratios of y over x. And so we talked about how we could find these ratios by dividing things away and making those ratios really visible. We also talked about an alternative strategy where we could substitute in first and then find our y over x ratio. Okay, so whatever way feels more comfortable to you. Here was sort of option number one, which it seemed like a lot of folks were feeling good about yesterday. And alternatively, you could sort of switch the order by doing what is on the right-hand side of that squiggly line. Now, one other thing that came up a lot yesterday was that as we are solving these questions, we have a lot of choices in terms of when we simplify and in what order we do that. And so that would certainly be a personal choice in terms of how you decide to simplify. But either way, you're looking for those ratios of y over x. And it turns out that when we use that ratio, we can create a situation where we need a the separable differential equation techniques from last week, okay? So today, we are going to take a look at something called Bernoulli's equation. Okay, and so these will be a little bit of a different flavor. And when we are doing these, what we're going to be looking for is the following. We are going to be trying to turn these equations into linear equations. All right, so that is going to be our goal from today. We'll not only get a chance to practice substitutions, but we'll also get a chance to review the linear equation solving methods from last week. Okay, so without further ado, let's jump into these examples and let's talk about what makes it a Bernoulli's equation. Okay, so one thing that you might see here is that we have something that looks like we have a dy dx. So we have a first order differential equation. And we might write this in a general form like this. We might have a y prime plus, this part should look familiar, but a p of x times y. Okay. But one sort of issue we have here is we have a y squared. And so that means that it's not linear yet, all right? And in fact, we could write this as having some function of x times y to some power. Okay, so the thing in the blue is like a general version of what we see above. And when we see that, we are noting that this is Bernoulli's differential equation, okay? So here's how we're going to approach these problems. We are going to approach these problems by getting rid of the thing that's causing the problem, the y to the n, all right? And so how do we get rid of those? We are going to divide by y to the power of n, okay? And so in this case, n equals 2 because n is the power of y, okay? So let's take this differential equation, let's divide every single term by y squared, and let's see what we get. So we divide, we get y to the negative 2 dy dx plus 4 over x, that part stays. And then this y, when I divide that by y squared, I get y to the negative 1 equals, the only thing I have left on the right-hand side is x cubed. All right, so we've divided that away. Now we get to use some substitution to help us solve, okay? So what we're gonna do is we're gonna substitute. Everywhere we see y to the n minus 1, so in our case, y to the first power, we're going to go ahead and let that be the letter u, okay? Now, just like we did yesterday, we're not just substituting in u, but we also have to substitute in a du, all right? So let's go ahead and find our u prime in a general form. And it turns out we can just use power rule to find that derivative. And so we will have n minus 1 to the y times y to the power of n minus 2. Okay, so those are sort of general form. But when we apply them to this specific case, we will end up with u equals y to the, let's see, 2 minus, this is 1 minus n. 1 minus n, that changes this. 1 minus n, and this will be negative n, okay? So 1 minus n will give us 1 minus 2 in this case, or we could call that y to the negative 1. And from there, we can find our u prime, which is going to be negative 1 y to the negative 2. And since we're using power rule, that's kind of why, if you notice in that division step, I kept it as a negative power, because the negative power makes it easier for me to see what my derivative is, instead of sort of converting it to a fraction and then having to convert it back to use power rule, okay? So now that we have our u and our u prime, we can substitute this into the equation that we found, all right? So turns out everywhere we see this, this y to the negative 2, we have this y to the negative 2. But there's something that I'm missing, something that I forgot to write. And sometimes as students, we sort of forget to write some parts, and then it makes the substitution harder. What did I forget to write after that u prime?
du.
Close. I don't need a du. I actually need a y prime. Okay, so when we're taking that idea of a derivative, if we have the du over here, then we have to have sort of that dy on the other side. Okay, and that's going to help us take care of this y prime right here. And so let's substitute everything in now. Since I have y to the negative 2 dy dx, I'm going to substitute that with, let's bump this negative 1 to the other side. I'm going to substitute that with a negative u prime. So all of this became negative u prime. Now my substitution only involves u's and y's, so I have to leave this plus 4 over x where it is. However, I can take that y to the negative 1 and everywhere I see that y to the negative 1, I can go ahead and put in a u. Right, so I've constructed the left-hand side now to only have u's and x's instead of y's and x's. And same thing, because I don't have a substitution for x, I'm going to keep the right-hand side as x cubed. Now, one of the things that we sort of work with a lot, we have our, du dx or u prime, whatever we want to call it, but life is generally easier when that is a positive value rather than a negative value. So I'm going to go ahead and take that -1. I'm going to divide my entire equation by -1. And that's going to give me u prime minus 4 over xu equals -x cubed. So what we've done right now is we've turned Bernoulli's equation into a linear differential equation, all right? Now, one of the reasons last week on the homework, I was like, I want you to tell me how you know this is linear, or how you know this is separable, or how you know this is exact, is because sometimes in the context of a bigger problem, we have to know what we're aiming for. Because if we can bring it back to these more fundamental types of differential equations, then we can solve so many other types, okay? And so we look at this, every coefficient function is only with respect to x. We're good. And instead of y, we're going to say u, because that's the letter we have. All of these, we have a first order, and this is to the power of 1. So we've made it linear, okay? And so now that we've made it linear, we can use the techniques we learned last week, find our differential equation solution, and then at the end, we're going to plug back in our y. Okay, so you can think about this like a very grown-up U substitution, right? The first time you learned U substitution, you're like, how am I turning this complicated thing into something more simple? We're doing the same idea here, except we're turning a Bernoulli's into a linear. All right, so let's go ahead, and when we think about a linear differential equation, so to solve a linear differential equation, let's go ahead and begin by finding our mu, our magical multiplying function, or our integrating factor. So mu of x equals, let's see, what was that equation? E to the integral of p of x dx, okay? Now, one thing I want to point out here is when we grab our p of x, if you just take 4 over x, you're going to be so sad about that. Okay, I will also be sad for you. The linear differential equation, by definition, has a plus sign in between there. So when we take our p of x, we need to define it as -4 over x. That's going to change our multiplying factor. So we want to make sure we grab the right p of x so that we get the correct mu of x. So e to our integral of -4 over x dx. This integral, I'll get e to the -4 natural log of x. Now this part, I do want to make sure we know how to simplify this. I know that the e and the natural log cancel out. But in order to use that, it's more helpful if I bump this -4 up as the exponent for x. In other words, e to the natural log of x to the -4. Now we can say e and natural log undo each other, and so we obtain an integrating factor of x to the -4, okay?
Hey, Judy, are we omitting the absolute value here because of the initial conditions, or how is that getting?
So if we look at our initial conditions, we're plugging in an x value of 2. An x value of 2. But we're also noting that x is greater than 0. And since it's defined in the problem that x is greater than 0, we don't have to consider absolute value because we've already said they're only going to be positive. Okay. All right. Now, one name for mu is the integrating factor. The other name is sort of a multiplying factor, right? So we're going to multiply through by our mu. So we're going to go to this linear differential equation that has u and x's. We're going to multiply by x to the negative 4. All right, so we've multiplied everything through. We've used our exponential rules or exponent rules carefully, where we are adding our exponents. And like I said earlier, I know I'm going to be taking derivatives or looking for derivatives, so it's a little bit easier for my brain if I leave them as negative exponents. All right. The beauty of linear differential equations is that left-hand side we can pack up as the derivative of the product of two functions. And so we might be able to write the left-hand side as the derivative of x to the negative 4 times u. Okay. I did see a small handful of people who on the right-hand side here actually wrote this. Okay. And so the mistake that those folks made is they said, well, they thought that they were taking the derivative of the left-hand side, and so they also took the derivative of the right-hand side. But that's not actually what we're doing. We're just rewriting this left-hand side as the derivative of a product. So for that reason, we don't need the derivative of the other side. We're only writing that as a derivative so that now we can take the integral of both sides. All right, we can take the integral of both sides, and the left-hand side just becomes x to the negative 4 times u.
Judy, I might have missed this, but it's negative x to the negative first because you took the negative and you placed it on the other side.
Yes.
Like you divided the negative.
I got my substitution and then I divided everything by negative 1 so that my u prime was positive.
Okay, thank you.
All right, now when we integrate, we only have x to the negative 4u on the left-hand side. And then we integrate the right-hand side. And that we might recognize is going to be a natural log. And to Christian's point earlier, when we write that natural log, we're not going to need the absolute value because the problem was already defined to say x has to be greater than 0. Okay. So we get x to the negative 4u equals negative natural log x. And I did have a few folks who forgot that plus c. Okay, so let's write that nice and bright in the pink. You want to make sure you have that plus C. It wasn't always as important in Calc 2, but if we leave out that plus C, we will not have anything to solve for, and then initial conditions don't seem to make sense, okay? Don't forget. All right, so we've taken our integral. I will leave it up to you whether you want to isolate your u. So quite a few of you seemed to like to get it into more of an explicit form, but either way is really fine, okay? So if I wanted to, I could divide both sides by x to the -4. So I would get negative x to the 4th natural log of x. Now here's the part you want to be careful about though. If you're going to divide that x to the -4 over, you better divide your c by that value as well, right? Because c is the number, but you're dividing it by a variable that's going to be changing. So you would have to write this as c x to the 4. Okay, so that was sort of another place where I saw a few people miss that. If you're gonna divide over, you have to divide every single term by that. All right, so we've solved our linear differential equation, and we are most of the way there because in our last step, all we're gonna do is put back in our y's and plug in our initial conditions so that we get a number for C, okay? So in our final step, we're gonna go ahead and sub back in the y and solve for C. All right, so we're gonna sub back in for y and we're gonna solve for C. So everywhere we see a u, we can actually replace that with y to the -1. And so what we're gonna get is y to the -1 equals our negative x to the 4th natural log of x plus cx to the 4th. Okay, so we substituted everything in, and now we apply those initial conditions. That means everywhere we see an x, we're plugging in a 2, and everywhere we see a y, we're plugging in a -1. Sometimes I like to write things like y to the -1. I'll write it as 1 over y when I'm going to start plugging in numbers. It just makes it easier for my brain to think about like computing those values by hand. And so if we plug in those values, we get 1 over -1 equals negative 2 to the 4th natural log 2 plus c times 2 to the 4th. If you've taken discrete recently, you know how important powers of 2 are. And so hopefully we know 2 to the 4th is not 8. Might happen early morning, but it's not 8. It's going to give us 16. And so we will have -1 equals -16 natural log 2 plus 16c. And I can either factor out the 16 right now, or I can just solve for my c. Either way is fine. Let's see if we get 16c equals 16 natural log 2 minus 1, and then c will equal natural log 2 minus 1/16. All right. Now we've done so much work. We found a linear equation from something that seemed seemingly not linear. We were able to apply techniques from last week. Then we plug in our initial conditions, we solve for C, and as a final answer, we want to make sure we just write everything in terms of X and Y, and we plug a number in for C, okay? You can go back to that Y to the -1 and leave it that way. All right, so as a final answer, I might write Y to the -1 equals negative X to the 4th natural log of 2, or X rather, plus C, my number for C, X to the 4th, okay? And that would be absolutely fine. Here's what else would be absolutely fine. I bet some of you would say, well, 1 over Y is equal to this whole thing, right? And so if you just take the reciprocal of both sides, you'll end up with your explicit solution. So Y equals 1 over this would also be an acceptable answer. All right. I think the most important part here is not that you get to the quote unquote most simple answer, but that you show me along the way, you know, how to get each of these steps. I think there are a lot of internet resources for differential equations, which is awesome, but sometimes people simplify things to a point and we're like so hung up on the simplification that we actually forget about the differential equation, okay? So let me get this question all on one screen for us. All right, before we move on to the next equation or example, are there any questions about example 4?
Can you explain how you got your U in step 1?
Yes.
1 and 2? Thank you.
Absolutely. Okay. So U in general, we're going to use this formula. U will be Y to the 1 minus N power. And so N.
Oh, okay. It's a
is
formula.
this-
Now
yeah,
I understand.
Yeah. Exactly. And that formula,
Sorry.
no, you're fine. That formula gets us to that linear differential equation. So we won't go through the derivation of that, but basically that particular formula will help us turn this Bernoulli's into a linear. All right, any other questions on example 4? You can always ask questions later. I know sometimes it's hard to think on right on the spot. All right, let's take a look at example 5. So we have y prime plus xy equals xy squared. And you know, this would be linear, except we have that y squared, right? That y squared is the problem. So the first 2 steps are really about helping us get rid of that y squared so that we can make it linear. And then we can use steps 3 and 4 to solve, okay? So our first step will be to divide by y to the power of n, which in this case is y squared. So we get y to the -2, y prime plus x. Let's see, y divided by y squared is y to the -1. And then this right-hand side just becomes x. Now, after we do that, then we want to use that formula to make our substitution, okay? And in particular, we're going to let u equal y to the power of 1 minus n, all right? So in general, we're letting u equal y to the power of 1 minus n. You also want to find your u prime here, all right? And so that will give us 1 minus n y to the -n y prime. And you can write that formula, or if it's easier for you, just find your u and just remember to find your u prime, okay? So in this case, u equals y to the 1 minus 2, or u equals y to the negative 1. All right, so it turns out we're using the same u as we did in the previous one. Let's find our u prime. We get negative y to the negative 2y prime. That's going to allow us to substitute very closely that first term. Okay. Now, just like last time, though, we might notice that life would be easier if we kept to this part and then just move the negative 1 to the other side. So we make our substitution. We get negative u prime plus xu equals x. And just like last time, life is easier when we keep that u prime positive. So let's divide everything by negative 1. And we get u prime minus xu equals negative x. All right. So far, so good? Yeah, okay. These two are the new parts. And then after this, we find our multiplying factor, we multiply through, we integrate, and so we go back to what we learned last week for our exact differential equation, or our linear differential equation. I'll give you a moment to find your mu of x for this. I think this is a great example of, again, of like, let's be really careful about the sign of our p of x, because that will impact our answer for the mu of x. All right. So we should end up with a mu of x of e to the negative x squared over 2. Okay, that negative sign there, definitely important, and it comes from p of x being negative x. Okay. All right, once we've got our mu, let's multiply our substituted differential equation in by that multiplying factor. And that's going to give us going to give us something like that. Okay. Remember that that left-hand side is the derivative of a product. And so we can rewrite that mathematically as derivative of the two functions And that d dx on the left-hand side does not mean we also need one on the right-hand side, right? All we're doing is rewriting it, expressing it in a way that will make integration easier for ourselves. And on the right-hand side, we have negative x e to the negative x squared over 2, right? Now, I know that sometimes when we're integrating and we see two different functions, like in this case on the right-hand side, I have x and I have e to the negative x squared over 2. Sometimes, because Calc 2 is more recent for us, we think, oh, this must be integration by parts. However, we really want to think, let's start simpler. Is there a simpler technique we can try before we jump to integration by parts? And as it turns out in this case, we can use a U substitution, okay? Now, since we've already used the letter U, let's choose a different letter. And let me write that integral first before we right? So when we're integrating that right-hand side, we're going to go ahead and set up a U substitution. So let's call that V since we already used U. And in this case, negative x squared over 2 might be a really good choice for that to be. That would give us the dv of negative x dx. All right. What does this give us? The left-hand side remains the same. And the right-hand side, well, the integral of e to the u is just going to be e to the u. So we get e to the negative x squared over 2. And let's do it in pink one more time. Don't forget that plus c. All right. Now, let's go ahead and let's isolate our u. And the reason why I'm suggesting this is I noticed that that coefficient of u, that e to the negative x squared over 2 is happening on both sides. So I might be able to write it in a more simple format. Right. In particular, the first term becomes a 1, and the second term becomes c e to the positive x squared over 2. All right. From here, let's go ahead, put back in our y's, all right? So we're going to put our y's back in. And in this particular question, we don't have any initial conditions, so it's completely okay to leave our answer with the C there, okay? Well, everywhere we see a U, we're going to put 1 over y. So we get 1 over y plus, or equals 1 plus c e to the x squared over 2. You are totally welcome to leave it like that. All right, you can leave your answer like that. I have no problems with that. If you've shown me everything else here, I am very convinced that you know what you're doing. Alternatively, like the last problem, you can say, well, I can get y by itself just by taking the reciprocal of both sides. And you could write y equals 1 over 1 plus CE to the x squared over 2. All right. Either one of those is fine. Just make sure you leave enough breadcrumbs along the way to convince this skeptical mathematician that you know what you're doing. Okay. All right, let me put this all on one screen. I know that the internet has been choppy, so in case there's anything you missed, you could take a quick screenshot right now. And before we move on, are there any questions about example number 5?
Judy, sometimes we consider C like towards the end. Like if there's anything with C, we kind of just say overall it's like a big C. Would it be okay to consider it here? Like just saying like 1 divided by 1 plus like C? Or should we rather leave the equation?
Oh, I see. Are you asking about this? Like, why can't we
Yeah.
just write that as a C? Okay, that's an excellent question. So that's C. C is a number, right? It's only a number. So we can only combine it with other numbers.
Okay.
But right here we have E, which is also a number, but X, that variable, that's a variable. The X is going to change. And so because the X is changing, like this X is changing, that means the exponent is changing, which means that
Which
this,
would make C change.
yeah. So if
Okay,
it was like, if it was just E, like C times E, you could change that into a C. That would be okay.
Okay. Thank you.
Mhm. All right. Any other questions here? All right. So we've kind of written this out before, but if we wanted to think about in general, how do we get from a Bernoulli's to a linear? We might say this, that we start with y prime plus this p of xy equals f of x y to the n. And the problem here is the y to the n. And so our first step will always be divide by y to the n. And that will give us y to the negative n, y prime, plus p of x, y to the y divided by y to the n means I can combine exponents and do 1 minus n, right? Power on the top is 1, power on the bottom is n. So when we combine, we get 1 minus n. And that's going to equal just f of x, okay? I forget who asked this wonderful question earlier, but someone was like, why are we letting u equal y to the 1 minus n? And it is precisely for this reason, because every time we divide by y to the n, we end up with a y to the 1 minus n. And so we're going to use that to be our u. All right, so this will become our u. Right. We've also noted we have to also confirm or convert our y prime. And so we need to find that u prime. And we can do that by using the power rule, where we bring the power down to 1 minus n as a coefficient, y to the 1 minus n minus 1, right? That's the definition of power rule. But because I have a 1 and a minus 1, that exponent becomes a negative n. Right, so we end up with 1 minus n y to the negative n y prime. Once we have that and we substitute everything in, we end up with 1 over 1 minus n u prime. And all I'm doing is taking this u prime and getting y prime by itself to make that substitution. Plus, the p of x does not change because my substitution is only with u's and y's. But that blue part becomes a u equals f of x. And now I have my linear differential equation. Okay, so if last week you felt like linear differential equations were challenging, this is a great opportunity to go back and practice those again in the context of something different. Okay. All right. Any questions on the Bernoulli's situation? All right. Well, then we will spend the rest of the time taking a look at our very last type of substitution. Okay. And in this one, we're going to get a chance to practice. I think there's one example that helps us practice partial fractions. Again, it's not because we're going to see a lot of partial fractions right now, but we will towards the end of the class. And so it's something I want us to feel pretty confident in. Okay. And so it turns out that there's sort of other ways that we can use substitution to get down to separation of variables. All right. If you ever take partial differential equations, everything is about using separation of variables to get partial differential equations to be ordinary differential equations, which is like the flavor of class we're taking right now. Okay, so all of these skills, if you plan to take partial differential equations, these skills will definitely be very helpful. Okay. All right, so let's take a look at this. All right, I see that I have y prime minus this quantity squared equals 0. And if I wanted to be more clear about is it going to be separable or not, I could turn y prime into dy dx and then multiply through by dx. And if I did that, I would get dy minus 4x minus y plus 1 squared dx equals 0. And from inspection, right, by looking at that, I bet we can tell it's going to be pretty hard to get the x's and y's to be separate. And so we're going to try and separate them by using a substitution first to make things more easy to separate. Okay. So let's put a red frowny face here because that's not so helpful for us. But if we use some substitution, I bet we'll be able to turn this into a separable differential equation. All right, so let's do that. Let's go ahead and say for step 1, make a substitution. Right? And in particular, I'm going to say, let's choose to take 4x minus y, and I'm going to give it a different name. Okay. So let's let v equal 4x minus y. All right, so that's the different name. We're going to call it v. V is 4x minus y. And if we're taking derivatives with respect to x, then we can say that v prime is equal to 4 minus y prime. All right, so anytime you're making a substitution, it's good to get in the habit of, I'm not only going to take care of the variable that I'm substituting, but also the derivative of that variable. All right. Now, let's go back to our original equation and let's substitute everything we can and see what we get. And we might notice that this part over here, y prime, what's another way I could say y prime?
4 minus v prime.
Yeah, use that algebra. We can solve for y prime and get y prime equals 4 minus v prime. And so everywhere I see the y prime, I'm going to replace it with 4 minus v prime. So 4 minus v prime is our y prime. Minus, let's see what happens inside the parentheses. I no longer have 4x minus y plus 1. Now I have v plus 1. And I don't just have v plus 1. Don't forget about that exponent. We have v plus 1 squared. Right. Now, if you're wondering where that dx went, we really hit it with the v prime, right? V prime is really dv dx, and so we sort of grouped it in there. Now, from here, I bet we can start to unpack this a little bit. So we're going to go ahead and get v prime by itself, okay? So we're going to isolate v prime, and so it'll equal 4 minus v plus 1 squared. And in fact, I'll write dv dx equals 4 minus v plus 1 squared. All right. This is a great chance to double check and just make sure you haven't made any sign mistakes, all right? But I think we're good. And now, if we multiply both sides by dx and we divide both sides by this 4 minus v plus 1 squared, let's see what happens. All right. Here's what we're going to do. Let's expand the denominator. Okay, so we're going to do a little bit of foiling. We're going to distribute that minus sign. We're going to be super careful about distributing that minus sign. Let's see what that gets. All right. Whoa, how we doing with that distribution over there? Distributing and foiling, and we get negative v squared minus 2v minus 3 in the denominator. let's see, 4 minus 1 is indeed plus 3. Good catch. I love it. Okay. Now, personal choice here, okay, in terms of this next step, I tend to like to factor when my leading coefficient is positive. Meaning instead of a negative v squared, I feel like my life is easier when it's a positive v squared. So one thing that I could do is divide both sides by -1, and I would get dv over v squared plus 2v minus 3 equals negative dx. Okay. Now, why would I want to factor? Let's see. When I factor, I get v plus 3, v minus 1 equals dx, right? So we've done all of this algebra. We've gotten down to something, dv over 2 separate factors, all right? Now, these separate factors are precisely what tells us, hey, we might want to use partial fractions, all right? Now, some of you might be sitting here going, I could have integrated without partial fractions. Anybody see some integration techniques we could have used instead of doing these next 4 lines here? One way you might want to try is the u sub. Okay, so I'll leave you to try that on your own time, but u sub should help with that integration on the left-hand side as well. And there may be other techniques out there, okay? The reason why I'm asking us to do this right now, again, is because I want to make sure we're good with the partial fractions piece, okay? All right, we ready for some partial fractions?
Sorry.
We need a,
Where did the -1 go for the dx?
This -1 that I forgot to write there?
Yeah.
Yeah. Yep, it's there. Thank you for catching that. Okay. Any other questions or kind reminders that I made a mistake before we move on? Okay. All right, so let's use this space down here to do some partial fraction work. Partial fractions. Okay. Partial fractions here, we really want to say 1 over v times 3 times v minus 1 equals some constant over v plus 3 plus a different constant over v minus 1. Okay. Does anyone happen to know why this numerator is a constant? And it's okay if you don't. For right now, we can just say it's going to be a constant. But as we get into more complicated partial fractions, I just want to plant a seed that that numerator won't always just be a constant. Sometimes we'll have like ax plus b or cx plus d, okay? And so it's not always just going to be a letter. It is in this case because our numerator should be 1 degree less than our denominator. So our denominator is a linear, so our numerator will be a constant, okay? All right, so life is always easier with questions like this if the denominator on both sides is the same. Because if the denominator on both sides is the same, we can effectively not worry about them and only worry about the numerator. Okay. So this left-hand side will stay the same. And let's kind of go back to some middle school or high school math. What do I need to multiply the first fraction by to get a common denominator with the right-hand side or with the left-hand side?
V minus 1.
V minus 1, good. And we're in fact going to say V minus 1 over V minus 1 because we don't want to change the problem, right? And similarly, for the second one, V plus 3, V plus 3. Now, once we've got both denominator or all the denominators on both sides equal, we say, I'm so glad I don't have to worry about you anymore. I'm only going to deal with the numerators. And so we get 1 equals a times v minus 1 plus b times v plus 3. Okay. There is a shortcut here that we can use to solve and find values for a and b. Okay. One thing we can do is we can be very clever about the numbers we choose for v. And if we're clever, we can make either a or b go to 0, and then we only have one variable to worry about. So for example, I could let v equal 1. That would mean everywhere I see a v, I'm going to plug in 1. And I would get 1 equals a times 0 plus b times 4. A times 0 goes to 0, so we can see that b is going to be 1/4, right? What might be another clever number to choose for v?
-3.
Yeah, we could choose -3. Then we're going to plug in -3 everywhere we see a v. So 1 equals a times -4 plus the b times 0. Oh, there's that 0. And we get a equal to -1/4. Okay. Now, I know that you folks have come maybe fresh-ish out of linear algebra. You're welcome to set up matrices here if you want to, or other ways of solving systems of equations, right? But when it's linear like this, picking clever numbers does make it go pretty quickly, okay? So for some of the more complicated ones we'll see later, matrices might be useful, but I think if it's a linear case, choose that clever number and then be on your merry way, okay? All right, now all of this is to say that we were originally working on a problem where we had to integrate, right? And the problem is when we have an integral like this, it's a lot harder. But if we can split this into two fractions, then we can integrate much more quickly, okay? So let's take a look at how this impacts our ability to integrate. You know, I don't mind like writing on a tablet because it does save notes and people can, you know, go back and look at it again and it's easy to post. But sometimes I miss like being in a classroom and just being able to see like 4 boards at the same time so you can keep track of all the work. That part makes me a little nostalgic. But now that we've separated, we can integrate, okay? And so what we have now is instead of the integral of 1 over v plus 3 times v minus 1 dv equals integral of negative dx, I won't forget that negative this time, we now can take the left-hand side and actually write it with our Where did it go? A over v plus 3 plus b over v minus 1. And we can plug in a as the value we found, which is negative 1/4, and b as the other value we found, which is positive 1/4. So that gives us the integral of negative 1/4 over v plus 3 plus 1/4 over v plus 1 dv, which equals negative integral of dx. And as gross as this looks, that negative 1/4 and the positive 1/4, those are just constants, right? So we can pull them to the front of our integrals. And when we pull them to the front of our integrals, we actually end up with negative 1/4, the integral of 1 over v plus 3 dv, and then plus 1/4, the integral of 1 over v plus 1 dv. Right. The nice thing about this is we've turned this fraction thing with two terms in the denominator into ones that only have a single term in the denominator. And with a very simple u sub, we can find that those integrals are just equal to the natural log of whatever the denominator is. And so we get negative 1/4 natural log of v plus 3 plus 1/4 natural log of v plus 1, v minus 1 equals negative, let's see, the integral of 1 is x plus c. All right, so we've done a lot of work so far, right? A lot of work here. One thing that we can do, we know ultimately that we've integrated, we've done the differential equation part, but we got to pack it back up so that we can get it in terms of x and y. Okay, so we want things with x's and y's, not with v's and x's. All right, and so therein lies some of the trickier parts. And again, there's a lot of different ways to kind of simplify from here, okay? So whatever method you choose, just make sure you can kind of justify how you got to where you go to, and that your work follows logically, okay? I feel like by this point, you're much better about, not proving, but just like demonstrating the fluidity of your work. There's a lot less magical math that happens at this level than like Calc 1. Sometimes they be pulling some magical stuff on me. I'm like, I don't know where that came from. But anyway, we want to get v out of here. So if you like, you can just take 4x minus y and stick that in everywhere you have a v. That would be one way to say, let's call it a day. Okay. So we could say negative 1/4 natural log of 4x minus y plus 3 plus 1/4 natural log 4x minus y minus 1 equals negative x plus c. And even though it's not pretty, this is technically an answer, right? We found our solution and we put it back in terms of x's and y's. It's very much implicit at this point, like the x's and y's are all kind of mixed together. I would say that this is fine. One thing that you might see people do is go ahead and get rid of that 4 by multiplying everything by 4. Okay, so that'd be like one thing people might do. What's another thing that people might do to simplify from here if they wanted to?
Can you combine the ln?
Yeah, a lot of people are like, I have an ln here and an ln here, and if I use my log properties, I can pack that up into a single natural log, right? So that might be another step that people take. And so if we did both of those, let's go ahead and multiply everything through by 4. And if we do that, we end up with negative natural log of this plus log of this equals negative 4x. Now I can't combine those because negative 4 or 4 times x is going to be 4x. But I can say that 4c is just going to be c. All right. So because I have a number and I'm multiplying it by another number, I can still call it a number. If we were to pack up our logs, we might say we have a fraction. Which one of those interior terms would go in the top and which one would go on the bottom?
V minus 1 should be on top, right?
Yeah. So we could have this one because this is the plus, and then the minus 1 means division, so that one would go in the denominator. Okay. People might leave it at this step. That would also be acceptable. Maybe looks a little bit cleaner, but it doesn't have to be. Okay. What's one thing that people might now be tempted to do now that they've gotten the natural log as a single natural log?
Multiply by e.
Yeah, we might raise both sides, e to that power, because then we would get our terms here, and then we would have e to the negative 4x plus c. And how else could I write this right-hand side? Let's talk about that simplification. How else could I express the right-hand side?
E to the negative 4x times e to the c.
Perfect. I'm so glad you said times e to the c, right? And then e is a number, c is a number. So we might just write that. Okay. You could keep going here. You could say, now I'm going to find a y value. That would be absolutely fine. Or you could kind of leave it here. That would also be fine. Okay. Our exams are not multiple choice, so they're not going to be trying to match an answer and like, did I do all the right algebra steps? All right. When I took Calc 2 in college, my college, like all the Calc 2 classes, every exam was multiple choice, except it wasn't like A through D, it was like A through double Z. And like every sign mistake you made was a different answer choice. It was terrible. Okay. So I don't want to do that to you, even if it would be easier on my grading. I want to make sure that we know what we're doing and that we understand what decisions you're making and why we're making them, or why people who write answer keys might write their answer in a certain way. Okay. So I feel like we've done quite a bit today. Here's what I would like to leave you with. Okay. There is one more example. And let's talk about a substitution for that. And I'll give you a goal answer, and then you can kind of use that for extra practice if you wish, because over the weekend, though I want you to certainly take some time and relax, we do have our first exam coming up a week from today. And so this might serve as an extra practice problem for you as you're studying for that exam. Okay. So let's take a look at this last one here. Right, y prime equals e to the 9y minus x. The substitution that I will suggest is that v equals 9y minus x. Right, that is the substitution that I will suggest for number 7. The goal answer is y equals 1/9 x minus natural log of 9 minus c e to the x. All right, so there's your substitution. There's your goal answer. And then if anybody would like to say, I want to practice with initial condition, let's say that we have the following initial condition. Y of 0 equals 0. I'm waiting for my screen to catch up. There we go, almost, come on, you can do it. All right, so our initial condition is y of 0 equals 0, right? You can sort of take this as far as you want. Here's your substitution. Here's a goal general solution. And then here is an initial condition if you'd like to practice finding a value for C, okay? I will tell you that your C should be a nice number, nice in a traditional sense that it will be an integer value, okay? So if you're getting some kind of fractions or radicals that don't simplify to an integer, something went wrong, all right? But your C value in this case should be an integer value, all right? So I will leave you here. Tomorrow's internet should be better. And then we can pick up there, okay? So have a great rest of your day. If you have any questions, I'll stick around for a couple minutes. Otherwise, be well, have fun, get outside into the sunshine.